In the previous lecture, we started the discussion on how to match a real load to a source that has some real impedance. And one of the possibilities that we had discussed was to replace the quarter wave transformer with some other means, for example, a literal step down transformer. And we had rather abruptly ended the discussion in the previous lecture, saying that the transformer could have some turns ratio that is a function of the source and load impedance. However, for various reasons, on-chip transformers or having a actual transformer at RF frequencies are not very simple. Does not mean that they don't exist. They do exist, but the techniques are not all that simple. So therefore, we said why not apply the concept of these lumped element matching networks, that is using LNC. So therefore, we have already discussed in previous lectures how to match a complex load to a real impedance using LMass networks. Which are L in shape. And they are made using LNC. So we had said that somehow can we use this LC for matching the real loads also. So suppose this is a source having source impedance RS, and that is to be connected to a load RL. So here is a transformer that we want to use, such that the impedance seen by the source while looking into this transformer should be equal to RS. That is for matching and for maximum power. So if we are able to use this LNC in some way, that is something we have to investigate. So therefore, let us apply then that LC concept or an L match network. So we can use series C, parallel L, or parallel L, series C. Multiple possibilities are there. So therefore, let us start with one possible example. If we can solve for one case, we can solve for others also. So let's suppose I have the same source with this source impedance, and I decide to use this network. A series C and a parallel L to match this load RL to the source. So effectively this is my transformer. So the point to note over here is that while RS and RL are purely real, this C and L are reactive elements. So therefore, this L and C are frequency dependent. So definitely the impedance that is offered by this transformer will be a function of frequency. That is for sure. But then, in spite of the fact that its impedance is a function of frequency, we can definitely try to have at least one frequency where we can do the matching. So we have to look for one frequency where effectively the impedances of this L and C, they are minimized in such a case that this resistance transforms into Rs. So at what frequency does the effects of L and C become least on the impedance? That is the frequency, that's the resonance frequency. That is the resonance frequency. So therefore, this part of the network is fixed, the source and the source impedance. So now we have some kind of a C, L and R network, and we have to hunt for that resonance. So while hunting for this resonance, we have to ensure that these R, L and C are somehow, forming a resonant network. So therefore, we have already seen there are two kinds of LC networks which can exhibit resonance very easily. That is a series network and a parallel network. So looking here, this network is neither series nor parallel. You have a series C followed by a parallel RL. So therefore, one thing that we can do is that we can transform this parallel RL into a series RL. So let's do that. So we will say initial network and transform network. So the initial network is something like this. And once we transform it at resonance, we will keep the capacitor as it is in the form of a dummy capacitor. Well, here it's not really a dummy. And this L and RL network, which are currently in parallel, they will become a series network. So the capacitor will not change, but this will become transformed. So let's call this as L prime and R prime. R L prime. So essentially, what should happen is that looking into this impedance transformer, as we want, the Zin should be equal to Rs. So here also this does not change. This is what we want. So therefore, we already know how to convert a parallel RL network into a series RL network. So let us write those formulae. So in that case, L prime will be a function of L, that is L Q divided by 1 plus Q square, and RL prime will be equal to R divided by 1 plus Q square. Right? So therefore, this will be RL. Yeah. So therefore, what do we want? So what is the impedance of this RLC network at resonance? That is nothing but Zin. And at resonance, the impedances of L prime and C will cancel out. So therefore, that will be equal to RL itself, which is equal to Zin, and that is equal to Rs, is what we want. So therefore, we can say that RL prime equals Rs. or this quantity. So therefore, Rs is equal to RL divided by 1 plus Q square, which means if you want the Q of the circuit, it has to be something like the whole root of this. So that means the Q of this RLC network must be this quantity. And we know that Q must always be a positive real quantity. So therefore, for this root to exist and be a real quantity, RL must always be greater than RS. So that is, this particular configuration, you want that the RL should be more than RS. Only then this will work. This will have a real value of Q. So now once we know the value of Q, we know the value of RS and RL, which are initially a part of the specification of the problem. All we now need to know is the value of L at C. So therefore, once the Q is known, so effectively you can show that for the series network, the resonance angular frequency that is omega 0, that will be nothing but 1 by L prime times C. And the Q of the network, as we know, the Q of the series network, that is nothing but omega 0 L prime by RL prime. So once we know the Q, we can easily find out the L value, and that is RL prime times Q divided by omega 0. Now we know that RL prime is actually equal to RL by 1 plus Q square. So if you substitute this over here, you will get RL times Q divided by omega 0 1 plus Q square. This is what it is. And if Q is sufficiently large, then this quantity will become almost like Q square, this sum, and this will approximate it to roughly Q by Q square will become 1 by Q. So you can use either of these formulae depending on what is the value of Q that is there, and Q again is a function of RL and RS. So this is L prime. So once you know L prime, you know L. So what you can say is L prime, that is equal to LQ by 1 plus Q square, that is equal to this quantity. So you can actually cancel this out. I'm sorry, this has to be q square. Yeah, so if you have this, you can leave it as it is. So then that means this q will come in the denominator, that is RL by omega 0 q, which is very similar to what we have got. So irrespective of whether the q is large or small, this is what you get. This is the value of L that you will need. And once you know the value of L, you can substitute it over here and get what is omega 0, and from that you can find out what is C. Let's do that. So omega 0, the resonance angular frequency, is equal to 1 by L prime C. So let's substitute that. So that means if I take omega 0 square over here, so this implies that C will now be, this will go in the numerator, 1 plus q square divided by L q square omega 0 square. This is the way you can find out the L and the C values. So we saw one example using which we can find out the required values for an LMass transformer, L-shaped matching transformer using L and C, to match some real load to a source having real impedance. So now, as I had mentioned in one of the previous lectures, that in general, depending on the values of the impedance, 4 kinds of LMass transformers are possible. So the first case is this, what we just saw. RL and RS. So we saw that this can only work when RL is more than RS. Another case for RL more than RS is when this L and C are interchanged. That is this. In a manner similar to this case, you can find out the required values for L and C also. The only difference is you will now have to transform this RC network from parallel into series while keeping L as the dummy element. The third case will be this. This will now work when RL is less than RS. Likewise, the fourth case is quite obvious when these two will be interchanged. For any of these two cases, what you can do is take these series RL network in this case and transform it into parallel. Here you can take the series RC and transform them into parallel and proceed accordingly. So this I leave to you as an exercise, which can also be verified using the Smith chart, wherein if this is my ZS in the center and, or let us say small rs, and this is my small rl which is normalized. So to move from here to here, what we can do is simply go this way onto the reactance circle, sorry, on the constant resistance circle, and hit the point where G becomes equal to 1, then transform to the G equal to 1 circle and then come over here. So this is nothing but a series inductor, and this is a shunt capacitor which is very similar to this. And as you can see, in this case RL is indeed less than RS because it is on the left hand side of RS. So what we had learned using the Smith chart for these L-shaped matching networks using reactive elements like inductors and capacitors, the same way we are verifying using the analytical approach also. Now, what we can see after all this discussion is that we have either a transmission line that is to be matched to a load, or we have a source and a load which need to be matched. Now all this discussion gives rise to another area of discussion, and that is the evolving of RF and microwave networks. So a network is defined as nothing but an interconnection of multiple elements. They can be RLC, they can be transmission lines, they can be diodes, transistors, so on and so forth. All electrical or electronic devices. So something tells us that, this kind of a source load arrangement is also a network, and they have this concept of input and output. So thereby we also introduce the concept of ports, which you may have learned in your basic course on network theory. So with this, let us now move over to bigger and better things. Armed with our knowledge of impedance matching and the basics and ideas of transmission lines, let us move over to the discussion on RF and microwave networks and analysis. So in its simplest form, a network can consist of multiple elements and has some things called as ports. So you can have, in the simplest form, a two-port network. Let's say port 1 and port 2. One can be the input, one can be the output. Now, in their most bare essential form, there is absolutely no difference between an RF network and any other electrical network that you may have come across in your previous courses of study, because they both work on the principles of electrical engineering, Ohm's law, Kirchhoff's laws, and so on. So it is wrong to say that the circuit laws cannot apply to RF networks. Definitely they can. However, the point is that we can apply the electrical laws or the circuit theorems only when the size of the network elements or the size of the networks is much small as compared to the wavelength. That is essentially what gave rise to the transmission line theory. Now, for a few moments, let us forget that we are dealing with this high frequency effect wherein the wavelength of the wave also plays a major role when compared with the size of the network. So let us now, for the sake of convenience, come back to our old network theory courses and try to see what are the parameters with which one can use to characterize or analyze the network in question. So some of these parameters you are already familiar with. If I have a two-port network, let us say the voltage at port 1 is V1 and the current that is entering is from I1. Over here you have something called as V2 and something called as I2 that's entering. So you already know some of the parameters which are very easy to work with, especially at low frequencies. One is called as the impedance parameters or Z parameters. The other is called admittance parameters or Y parameters. So the voltage and current at the two ports can be related using matrices and a linear combination of what are called as the Z parameters. So let us say the voltages can be related in this fashion. And with admittance parameters, you can express the current in terms of the voltage. Both are consequences of Ohm's law. Here the parameters are called as Y parameters. Times V1 and V2. So these Z and Y parameters are functions of the impedances or admittances that are part of this network, whatever they may. The question is, how can we find the Z parameters or the Y parameters? So for example, over here we can write V1 is Z11 I1 plus Z12 I2 and V2 is equal to Z21 I1 plus Z22 I2. So if I want to find out Z11, I need to make I2 as 0. So I can say Z11 is nothing but V1 by I1 given I2 is 0. And how can we make I2 as 0? We can make I2 as 0 if we make the port 2 as open circuit. So if you want to find out Z11 and Z21, you need to make I2 as 0. If you want to find out what is Z12 and Z22, you need to make I1 as 0. So therefore, this can be found out by making either of the current 0. So therefore, these are also called as open circuit parameters. Why open circuit parameters? Because you need to nullify the current on either port, and you can only nullify the current at either port by making them open circuit. And that is what is the basis for the Z parameters. Likewise, for Y parameters, you can say I1 is Y11 V1 plus Y12 V2 and I2 is Y21 V1 plus Y22 V2. So if I want to find out, let us say Y12, that will be I1 divided by V2, but V1 should be 0. So to find out Y11 and Y21, you need to make V2 as 0. But to find out Y12 and Y22, you need to make V1 as 0. So the voltage at either port now has to be nullified. And how can you nullify that voltage at some port? You can do so by replacing that port with a short circuit. So these are also called as short circuit parameters. These are also called as short circuit parameters. Now, this is something you already know. This is something you already know. So let us say, I'll not get into the analysis more because that is something you already know, but rather we will discuss some properties of the Z and Y parameters or matrices. So the first property is if any of the elements in the Z matrix or Y matrix is real, that means the network has resistive or conductive elements. Okay, so therefore the moment you see that network has a resistance element or a conductance element, it means those elements will dissipate power. So therefore the network is lossy. This means the Z matrix or the Y matrix have real values. This means presence of some R or G component in the network. And that means this is a lossy network. This is a lossy network. Now, if these Z or Y matrices are symmetric matrices, that means if the transpose of the matrix is equal to itself, if the transpose of this matrices is equal to the original matrix, that means that the network is reciprocal network. The network is reciprocal. So, as you know, reciprocal or reciprocity is defined in the following manner. If there is some current I at port 1, suppose I have this network and I am feeding port 1 with some current I, and at port 2 it produces a voltage V. This is port 1, this is port 2. And on the other hand, if I now feed the same current to port 2 and this produces some voltage V at port 1. So here it is, this is input, this is output. Here this is input and this is output. If this same current at port 2 is able to produce the same voltage at port 1 as it did in the previous case, then this is called as a reciprocal network. And that is very, very important. In some sense, it means it's a bidirectional network and it can work in the exact same way. So most passive networks are indeed reciprocal. So, or rather I should say that reciprocity is easy to find in passive networks. So now let us, having established this discussion, let us go one step further. Let us go one step further. And that is, how do we measure these Z and Y parameters? We measure the Z and Y parameters by either open circuiting some port in case of Z parameter or by short circuiting some port at Y parameters. That is what we do. Now, let us introduce RF. Let us say I have an RF network that is having two ports. And this is port 1 and this is port 2. Now suppose I want to make port 2 as an open circuit. So therefore, let us say I am giving some input over here and this one I am keeping as open circuit. Is it enough? No. Because as you see, there is some finite length of these two conductors. So therefore, from the point at which we are measuring versus the point at which these are entering the network, the two are different. If I am open circuiting this point, it does not mean that the current becomes zero everywhere. Now, this port line will start behaving as a transmission line. And transmission line will see some open circuit load. So the current will be zero only at this, across these points, not necessarily over here. Because the impedance will now get transformed. It will be some imaginary quantity. So therefore the voltage and current will both be non-zero. Now this is a point. On the other hand, if you had compared this to a low frequency network, making this as open circuit means the entire line becomes open circuit. But at RF, open circuit means only that point is open circuit. You cannot say for sure, or mostly that will not be the case for the rest of the line, because this will start behaving as transmission lines. The port feed lines start behaving as transmission lines. Right? So this is a problem. Likewise, if you have a short circuit, it means a short circuit will exist only at that point. At other points, there will be some impedance, so there will be some voltage and some current on these lines. So now, this is one of the major reasons why measurement of the Z parameters or Y parameters are difficult at RF frequencies. Because the notion of open and short circuit is kind of lost. So, having said that, are there any other problems? The second problem is you do not know what is inside that network. Suppose this network has an amplifier which is getting some input and it's giving some output. Now I want to measure its Y parameters and I conveniently make the output as ground. What will happen? So whether it is RF amplifier or a low frequency amplifier, the consequences could be disastrous. Because if you ground the output of an amplifier, you are essentially loading it. And therefore this will try to draw very high current and therefore the amplifier could get damaged. So therefore again, open or short circuiting is to be done very carefully. So therefore, if we want to do the analysis for RF networks, what is it we can do? Because now the open and short definitions have become rather meaningless, because at RF, open or short means only at that point, not across the whole line. The whole port does not become open or short. Why? So what is it that is causing that open and short to not behave the way we want them to behave? And that is the waves. Whenever we have an open wave, when we have an open circuit or a short circuit, we have a pair of waves. One is the forward wave, the other is the reverse or the reflected wave. So because of these, the voltage and current at other points are not zero. So what we can do is, rather than trying to forcibly connect an open or short and try to make either the current or the voltage zero, we can try to nullify either of the waves. We can try to nullify either of the waves. Preferred RF approach, that is make either of the waves nullified rather than the voltage or current. So let us now define an N-port RF network. Because in general, any network can have n number of ports. Let us say I have a port 1 over here. Let us say somewhere here I have port 2, and so on until I have port n somewhere over here. Now let us define some conventions. The wave, the voltage wave that is entering a port is called as V1 plus, and the wave that is leaving port 1 is called Vi minus. Likewise, this will be V2 plus and this will be V2 minus. Here we will have Vn plus and this as Vn minus. So in general, for 1 less than I less than n, Vi plus and Vi minus denotes the wave entering ith port, and Vi minus denotes wave leaving ith port respectively. So now that we know the property of transmission lines, or we know the property of these waves on transmission lines, why not try to relate the two of these? Rather than trying to equate voltage and current, why not try and correlate the two voltages? So then we can say that let us try to express the outgoing waves as a function of entering waves. Entering waves. So let us say let us say for any ith port, the Vi plus can be defined as some forward voltage times e raised to minus j beta x, and Vi minus can be defined as some V backward times e raised to plus j beta x, as we already know in terms of the solution for the transmission line equations. So with this, we define two matrices. One is called as the V minus matrix, which consists of all the outgoing waves, and that is an n:1 matrix. That is V1 minus, V2 minus, all the way till Vn minus. This is an n×1 matrix. And we also define V plus, which is a collection of all the entering waves. That is V1 plus, V2 plus, all the way till Vn plus. This is also an n:1 matrix, n×1 matrix. Now, to correlate the V minus as a function of V plus, we define it in this way. So this V minus equals this V plus matrix into another matrix. So if this is n×1 and this is n×1, we define this. The size of this definitely has to be n×n. And this matrix we call it as S. And if you expand, you will get this n:n matrix looking something like this. Times this V plus matrix. So this matrix is called as the S parameter matrix. Just like how we define Z parameters, Y parameters, whose size is n×n, where n is the number of ports, this matrix is called as the S parameter matrix or the scattering parameters. S stands for scattering. So now, the name scattering comes because if you have this kind of a port and there are multiple waves which are entering and leaving, it is thought that there is some kind of a physical phenomena because of the interaction of these waves and the network properties. So the effect that happens is often called very similar to what scattering is in physics. So therefore the name scattering comes. Now the question is, even if you define it in this format, what is the big deal? How have we been able to circumvent the problem of having to deal with open circuit or short circuit, which are useful only at low frequencies, not at high frequencies? Well, let us see. Let us now ask ourselves, from this equation, how do I find out some S parameter? I have an n×n matrix. How do I find out an S parameter? How to measure or find an S parameter? Well, suppose I look at some ith row and jth column. So therefore this Sij is something we need to find. If you look at the previous matrix, each of the V1 minus can be expressed as a linear combination of these S parameters and the V1 plus. So therefore, if I write V1 minus, that will be equal to S11 times V1 plus S12 times V2 plus all the way up to S1n Vn plus. So therefore, if I want to find out what is S12, what I need to do is I need to have V1 minus divided by V2 plus, but then all the others must be made 0. So that means all the other Vn should be 0 where n is not equal to 2. Apart from V2 plus, all the other V pluses must be 0. So likewise, any Sij parameter can be found out as Vi minus divided by Vj plus, and Vn plus has to be 0 where n is not equal to j. So effectively it is a ratio of the outgoing wave at the ith port and divided by the entering wave at the jth port, right? So now, if I have that n-port network, and this is port 1 and this is port 2 all the way till port n, and I want to find out S12, that means I am looking at V1 plus and V2, I'm sorry, I'm looking at, I'm looking at V2 plus and V1 minus. Forgive me. This will be so now if I want to find out S12, I need to make V1 plus, V3 plus, V4 plus all the way to Vn plus all as 0 for S21. I'm sorry, for S12. So for S12, we need to make all of these as 0 except V2 plus. That means this can be there. How can I make V1 plus as 0? How can I make Vn plus as 0? What you can see is there is a V1 minus which is coming out of this port and a V1 plus that is entering this port. So now if this transmission line at every port has an impedance Z0 and I connect a load over here where ZL is equal to Z0, then I can effectively say that V1 minus will be there, but V1 plus will be 0. So effectively, I am nullifying this wave. I am nullifying V1 plus. Likewise, at all the other ports except port 2, I can connect this match load. So therefore, what I am effectively doing is that I am using my transmission line theory and connecting every port to a match load and thereby disabling the wave that is otherwise thought to have been entering the port. So we are not at all using the open or short circuit techniques, but rather we are using the technique of nullifying a wave. So therefore, if I want to find out Sij, then every port except the jth port must be connected to a match load. This is the technique. Now, obviously, since we are assuming that the characteristic impedance of every of the port lines is Z0, therefore Z0 has to be a function, or the S parameters are functions of Z0 also. Now the question is, how can we find out the Z0, or how can we find out these parameters? So let us say I have a two-port network. Let us say I have a two-port network whose Z parameters are known to me. Then in that case, from the Z parameters, I can very easily find out what the S parameters are. How? So I'll say conversion from Z to S parameters. So as you know, the Z parameters can be related using these three matrices, where V is the n cross 1 matrix of all the voltage values at the ports, I is all the current values at values of all the ports. Both of these are n cross 1 matrix, and Z is the impedance matrix, which is n cross n. Now, if I have a port and say this is the voltage at some port V1, in terms of the transmission line theory, we said that this will have some V1 plus and V1 minus. So as per the telegrapher's equations, or as per the solutions for the voltage on the transmission line, we have established that the V of x is equal to some V1 plus, or sorry, Vf plus e raised to minus j beta x plus Vb times e raised to plus j beta x. And this is nothing but V1 plus, and this is V1 minus, and that is V1. So therefore, all the voltage vectors can effectively be expressed as the algebraic sum of the forward waves and the reverse waves. So therefore, I can say that this voltage matrix can be expressed as a sum of the forward wave and the backward wave matrices. Right? And likewise, the current is what? Current is 1 by Z0, where Z0 is the impedance of this line, times V plus minus V minus, which is nothing but an extension of our transmission line theory. So therefore, if I now substitute these equations over here, what do I get? If I put V, this equation, I will get this. That will be equal to 1 by Z0 times the Z matrix times V plus minus V minus. Now look at this quantity. It is 1 by Z0 times the impedance matrix. So it's like saying every element in Z matrix will be divided by this Z0 quantity. So that's like saying this, I can actually call it as small z matrix, or the normalized impedance matrix. So therefore, what I get now is that is equal to small z times V plus minus V minus and what we can do is we can now try to group those matrices with similar coefficients. So now, just like how this small z is an n cross n matrix, let us multiply the left hand side by the n cross n identity matrix, because multiplication with identity matrix does not change anything. So if this I is the n cross n identity matrix, then we can say I times V plus I times V minus is equal to small z times V plus minus small z times V minus. So let us try to bring the plus, V plus over here and the V minus over here. So therefore I can say z plus I times V minus will be equal to z minus I times V plus. Now, to isolate V minus at the left hand side, what I can do is I can essentially multiply the whole equation with the inverse of this matrix. As you know, the multiplication of a matrix by its inverse gives you an identity matrix. So if I multiply this whole equation, both sides, by the inverse of this matrix, then what I will get is V minus will be equal to now V minus equals something times V plus. So therefore this is my S matrix. This is my S matrix. So therefore I can say that S equals small z plus I inverse times small z minus I. This is how you can obtain the S parameter matrix from the Z parameter matrix by normalizing the Z parameter matrix. So we shall continue from this point onwards in the next lecture. Thank you.